So next up, we have Hoda Aghaei Khouzani, who's a PhD student at the University of Delaware. She's broadly interested in thinking about runtime optimizations, security, and reliability of non-volatile memory. And in particular, she will be on the job market this year. So if your university is recruiting, please get in touch with her. And today she will be talking about how to securely delete data in solid-state SSDs.
So hello everyone, my name is Hoda, and as Dr. Rodriguez said, that I'm going to introduce you a secure data deletion scheme for solid-state drives, or SSDs. This would be the outline of my talk, and I'm going to start with an introduction on why we are focusing on SSDs. As you may know, SSDs are becoming the dominant storage system in many computer devices, as from very small, like your small devices like smartphones, to very large data centers, mainly because they are very high, they have higher storage density than hard disk drives, they have a better energy consumption, they have better access latency. But the thing is, SSD has this unique property of remap on write, which can be considered as a security or privacy threat. This remap on write property creates a trail of a previous version of data, which we call them invalid data. So let's see how this invalid data can be a threat. Consider a coercive attack in which the user has to disclose both key and the data to the attacker. What is the data on SSD? The data on SSD can be includes valid and invalid data. While user accesses valid data, the invalid data is not aware of the existence of the invalid data, which can be a privacy threat. So the best defense strategy would be that the SSD vendors has to provide this secure deletion scheme, give this ability to the user to trigger this scheme to make sure that the invalid data is deleted from the disk. Now let's see how this invalid data actually created on SSDs. SSD has two basic operations of write and erase, which write is going to change ones to zeros, while erase is going to change zeros to ones. This can make a problem when the erase is done at the granularity of blocks, while write are done at the granularity of pages. So, for example, if I have this kind of data on my SSD, and if, for example, I want to update something on block 0, I have to copy everything else somewhere, then erase the block, and then copy everything back to the block 0, as well as a new version of the data, which means that it's going to be very time-consuming and energy-consuming. So what they propose is, they say that why not do updates out of place, meaning that when the update comes, they have to first write the new version into someplace new, and then invalidate the old version. Invalidating the old version does not mean deleting the old version. It means that the data is still on SSD, but it is not accessible through user interface. So let's see when this invalid data actually deleted from SSD. There is this garbage collection property procedure on SSDs, which is in charge of deleting all the invalid data. What basically garbage collection does is when it's selected block, it first copy every valid pages to someplace else in the SSD and then erase the whole block. Although this is actually there in SSDs, but it might be too late from privacy perspective, because the purpose of doing garbage collection is to empty new blocks for upcoming requests. So our goal here is that we want to securely delete all the invalid pages at user request, not whenever the disk wants it. And then we want to make sure that valid data is still accessible to the user. And the actual goal is that we want to minimize the cost of this operation. Remember in the previous slide, when we want to do the garbage collection, we have to move all the invalid data, which is going to be the migration of the valid data across the disk. And then we have to erase something. Here we have a k in our a k integer, which is going to show that erase is much more costly than migration. Previous work on SSD usually can be like categorized into three groups. The first one is sanitation, which basically they are like trying to erase everything. They don't care if the data is valid or invalid. They just erase everything and just make sure that nothing is on the SSD anymore, which is far from what is our goal. The next type of group called scrubbing. What they do is they target invalid pages, but what they are trying to physically reprogram that page because if you remember, writes changes ones to zeros. So they are saying that why not changing the rest of ones in the page to zero so the page is not going to be accessible. But the point is there is this program disturb effect in SSDs, which if you do such a thing, the valid neighboring data may not be accessible anymore. And the last set of works are trying to encrypt files, delete the key, and then they think that the data is not there anymore. But the problem is, with this kind of approach, you are not able to delete invalid pages. You are only able to delete the valid data of a file. So what we are going to propose, and I'm going to start with a motivative example. Let's see if we have such data on our SSD. And the very intuitive solution is that why not erasing just the blocks that containing invalid pages? With doing so, we have to first migrate all the valid data, which is going to be 14 migration in this case, and then erase all the blocks that contain invalid pages. It is going to be quite costly. The next approach that came to my mind is that why not encrypting data and then deleting the keys of invalid pages? If I want to store one key per each page, the overhead is going to be a lot. So why not group pages together? In this case, we group the pages at the same position in the block together and encrypt all of these pages with one key. So for example, in this case, we only need 8 keys for all of our data. So now, if I want to delete an invalid page, I have to erase the key. But you see, here we have the invalid pages and valid pages sharing one key. If I erase the key, the valid pages are not going to be accessible. So I have to first migrate those valid pages, which is going to be first, I have to decrypt it with the old key, encrypt it with a new key, and write it back into someplace else. And I have to do this for all the invalid pages. And then I would be able to erase those keys because the valid data are still accessible. In this case, we still have 15 migration and 1 erase, which is not good enough. So I thought, why not combining these two together? And we call this scheme ErasuCrypto. In this scheme, we are saying that let's first start choosing which blocks to erase and which keys to delete. For example, in our example, we are choosing the first block for the erasure-based scheme, meaning that we are going to migrate the valid pages and then erase it. And then when we have to only delete the keys for 2 rows, not all of the rows. So we have to do deleting the key for row 3 and row 7, and then we have to write back the key into the place, which is going to be 3 migration and 2 erase, which is quite better than the other 2. Okay, the question is, in this kind of a scheme, you have to make sure you select the best combination of blocks and keys for erasure and deletion. What we did first, we tried to formalize our problem. We said that, okay, let's convert this solution to a matrix of a status and then say that, okay, invalid pages are shown with 1 and valid pages are shown with 0. Then I said, okay, I have 2 other vectors. The first one is the D block, which shows that whether the block is chosen for erasure or not. And the second one is D group, which means that if the group is selected for its key to be deleted or not. So our constraint, if you remember our constraint, which was deleting all the invalid pages, can be translated to this. If the state of the page is 1, which is invalid, either its group or block should be selected for secure deletion. And then the cost can be translated into this, meaning that migration means that if the state of block is 0, you have to, if one of its group or block is selected for secure deletion, meaning that you have to do a migration. And for erase, simply you have to count the number of ones in the vector D block. Solving this problem is going to be really complicated. So what we thought is, why not changing it to a very well-known problem of maximum edge by click in bipartite graph. And for those of you who may not know what is this problem is that if you have this bipartite graph and if you want to create a biclic out of it, you have to remove these vertices and these edges to make sure that in the remaining graph, each vertices in one set is connected to all the vertices in the other set. So here, back to our matrix. What we did is said, okay, let's have one vertices per each group in one set and have one vertices per each block in the other set, and then we connect each node together. If we have a valid page, we are going to connect its group to its block, and I have to do the same thing for everything. And you remember we have this k factor in our equation. To implement this k factor and consider it here, we are going to add k extra group to both our matrix and our graph. Here, for the sake of simplification, I choose k equal to 1, but later in the results, I'm going to change this. So now you can see that this is if you find the maximum edge biclic problem in this, the remaining nodes are going to ones that we can choose for selecting for erasing or deleting, which is going to be the same as the ones that I show you in the example. Hopefully this is a well-known problem, and it has, although it is an incomplete problem, there is an OE heuristic solution to this problem. Let's go to our results. I implemented all of these schemes in disk sim and the SSD model provided by Microsoft. We used the Microsoft real-world traces that they collected from their servers. And then what I did is try to compare these. The first two are the two intuitive solutions. The third one is our proposed scheme, and the last one is the optimal because it's ILP. And now let's see. I consider k as to be 7 because the latency of erase divided by the latency of migration is almost 7. And then, as you can see, we get a very close to optimal result here. So it shows that this algorithm works well. This cost actually can be translated into migration and erase. And let's see what happened in the result of migration and erase. I provided these two graphs for you. And as you can see, erasure base always has the worst number of erase because it just erases the blocks. And then we have the cryptography base. It has the lowest number of erase because it only erases the key blocks. It doesn't need to erase the valid pages, invalid pages. And then, as you can see, that the number of migration depends on the distribution of the valid pages. In some of our benchmarks, the distribution of valid pages are like somehow gathered in blocks, while in others they are like gathered in groups. So it depends on the benchmark. You can have different values for the two schemes, but for us it's always getting the best results. And if I want to translate these to energy and latency, you can see that we can get 36% of energy reduction and 55% of latency reduction. To summarize, what I did is that we try to address this secure deletion problem in SSDs, while others' approach was costly or either they lose the valid data. We were able to resolve this issue, and our goal was to still keep the valid data and minimize the cost. And we combined the two basic solutions together, converted to a well-known problem, and then you can see that we achieved the near optimal results. And thank you for listening.